Okay. Large enough, or maybe I try like this. Yeah. Okay. Let's do like this. Okay. So basically, we're gonna look at what happens when you use the smart contract on the left. So obviously, the smart contract on the left has no functionality whatsoever because we didn't do anything. But somehow already a lot is happening, which is the part that's always happening, which is why it's interesting. So, because given that it's in the empty smart contract, it's basically in every smart contract on Solidity, on Ethereum. Given that basically every smart contract is compiled with the Solidity compiler. So. Yeah, we have, what do we have? So for those who are not so familiar with Solidity, we have a constructor which is going to be executed in when we deploy the smart contract on the chain, and we have an empty function f. And on the right hand side we have the EVM bytecode, which is not really the bytecode as we'll see in a second, but kind of the bytecode, what's basically the output of the compiler. And I'm using compiler 5.5, which is pretty much the most recent one, apart from like a small bug fix, but it's not so relevant here. Let me just cancel my notifications also. Yeah, so I'm using 5.5. So basically what happens? So first of all, on the right hand side, the first thing we see, so when we scroll through this, there's like a bunch of things happening, and we kind of see two blocks of text. So if we have this first block here, and then we have this sub-zero here. So we just have one contract. Why the hell do we have two blocks of assembly? Well, the first block is the constructor, and the second one is the actual runtime. So the runtime is what's in the end going to be deployed on chain, whereas the constructor is only going to be run once and not going to be deployed, like the code is not going to end up on chain. So yeah, now that we figured out that this is the constructor, we can kind of go through and see what's happening. So the first thing that's happening is this weird mstore operation. So just a brief recap. So every time we start any EVM operation, we get a fresh memory, we get a fresh stack, we get so we get a fresh execution environment, and now we store something in memory. So at address 0x40, we're storing the value 0x80. So why the hell would we want to do this? For this, what's the internal memory layout of the EVM? Well, basically there's none. It's completely undefined. It's just one huge blob of byte addressable memory. But what the Solidity compiler does is it kind of splits it up into these chunks. So first of all, it's logically split up into 32-byte chunks by how much gas you pay, but we'll come to that in a second. But otherwise, it's basically byte addressable. But the Solidity compiler typically works on 32-byte blocks on it. The first 32-byte block is a scratch space, so it leaves this free for things that we'll discuss later, same as the second block. The third block is the one we just saw. So in the third block starts at 0x40. So the third block holds the free memory pointer. The free memory pointer is basically the first address in memory where that's considered free, where new data can be written to. Then afterwards is the 0 slot. We'll also discuss that in a bit. And then finally we have 0x80, which contains the where the actual data will start. So what could an example of this look like? So we have, I mean, the scratch space will typically be empty. And now, as we saw, right, we wrote the value of 0x80. So on the right-hand side are now the values that are stored at these addresses. We wrote the value of 0x80 to 0x40. So that's now standing here. That's the M store we just did. And basically, then here would be the next data. And if we now would write any data, then we would write it here. And we would increase the memory pointer to by another 32 bytes. However, this is all convention, right? Nothing of this is happening automatically. This is just convention. So this, of course, brings a number of questions. So first of all, is this wasteful? Second of all, is this clever? Third of all, should we ever clean up any memory or not? And fourth, does this mess with compatibility? So we'll briefly talk about these here. So first of all, I mean, often when we think about smart contract execution, we think about how efficient is something in terms of gas. And here we are allocating space in the memory, right? And we might not even be using it. So as we'll see later, our empty contract, it writes into memory, but it never has to do that. So it's actually wasteful, right? But how bad is it? Well, we are here, realistically, we need three, so with memory, we're always paying for the last block we're using. And here we need 3 blocks of memory because we're writing to the third one. And per block of memory, we're paying 3 gas, which is nothing. So, I mean, just in relation, yeah, it's a super tiny number, right? It's like, so we're paying 9 gas. The minimum transaction cost is anyway 21,000 gas. So this is like a really small amount. So is it wasteful? Yes and no, because as we'll see later, we are actually wasting this, right? And by the way, for the more knowledgeable ones, I compiled this bytecode that we're looking at with Optimize. So these things are not being optimized out. But yeah, it's not super wasteful. Second question, is it clever? So why the hell do we even have this weird layout? So we're leaving this scratch space in the beginning for a lot of inline assembly operations and so on. And it's frequently being used, and it makes these inline operations a lot easier to do because they don't first have to check where the free memory pointer is and then increase it and write there and so on and so on. They can just use this space in the beginning, which is quite useful and generally I think a good idea to have this scratch space. Should memory be freed? So currently the Solidity compiler only ever allocates more memory. It never frees any memory. So how does memory get freed? Well, at the moment that our EVM instance stops, all the memory is basically gone. So but we're not freeing it explicitly. Could be done, but basically they don't really care. And as we said, reserving an extra slot of memory just costs 3 additional gas, so they don't care and they just reserve more and more memory. And the final question, does this mess with compatibility? So if I decide to have this memory layout and someone else decides to have a different memory layout, and actually the memory layout used to be different, so old compilers will produce a different memory layout. Does it mess with compatibility? And the question is no. The answer is no, because all these things are internal, right? And they're not exposed to other contracts. Only this contract can access its memory. So yeah, the good thing is at least the crazy things we're doing here do not mess with compatibility. So we saw that we stored this free memory pointer, and I'm kind of like prefetching this here, but we'll see that we're still inside the constructor, right? We'll see later that we're never actually we'll never actually use it. So it's completely wasted here. So what this notation is hiding is that we first push these two values to the stack, and then we did this M store here. So like these three operations are completely wasted. And they are wasted inside every constructor, right? So, well, not inside every, because some need the memory, but I would say inside the majority of constructors. Then next thing is we have this call value. So call value gives us the amount of ether that was given to this message call. So amount of ether, well, because also while creating a contract, we can already give it some initial ether. And so this will just put the amount of ether on the stack. So now we have on the top of the stack, we have the amount of ether. So now comes the dupe1 operation. So dupe1 takes the top of the stack and duplicates it, hence the name dupe1. Dupe2 would take the second element on the stack and duplicate it, and so on and so on. We'll have another quick discussion about dupe1 in a minute. So basically now we have the value on the stack twice, and for the topmost element we'll now do the is0 operation. So basically we'll ask ourselves, is the topmost element 0 or not? And in most cases it will be, because typically we are not giving ether when calling a constructor. So let's assume for now that it is 0. So then is0 will return 1, and it has consumed one of the two call value operations, right? And this is another push. So here this assembly is using tags, right? So we see this tag being referenced here. The tag is basically a jump label, so it tells us where we're jumping to. So we're pushing the tag on the stack, and then we're jumping to that location. Jump, that's a conditional jump, right? If the condition is true. So we said that is0 will most likely return 1. So if there's a 1 in the second position of the stack, we're jumping to the first position of the stack. The first position is currently tag 1, so we'll jump to tag 1. Now both of these got consumed, but we still have the call value on the stack from the dupe1 here. Now it turns out we actually never needed this, so we're taking it off the stack. So again, something which is kind of wasteful. So we kind of concluded by now half of the constructor we didn't really need. Now comes the part that's actually doing something. So I'll scroll down a little bit so we see it. So basically, this is not a real EVM operation, it's what the constructor writes in here. We are pushing the amount of bytes that our bytecode is long, the sub-0 that I mentioned, which is standing below. We're duplicating it, we're pushing the amount of, we're pushing where the offset is inside the message call that we just made, and then we're doing a code copy. So basically, we can summarize all of this as copying, because when we want to create a new contract, we include the code inside the transaction. Where, like, the bytecode is the data inside the transaction. This takes the bytecode out of the input, kind of, and the code copy with the right sizes and the right offsets and so on, and copies it into memory. So now we're actually writing into memory, but we actually overwrote the code pointer above, but we don't really care. And then finally, we're doing the return here. So there's a convention in the EVM that whatever the constructor returns is going to be written as the code segment of that contract. So the constructor returns an offset. The offset is going to be 0 here. That's why we're pushing 0. And a size, that's going to be this data size here. That's why we duplicated it before, because now, I mean, keeping track on what's where on the stack is always a bit tricky. We can later look at it again in Remix. but yeah, that's why we have the kind of the data still, the right data still on the stack. So in the end, we return 0 because and let's say 50 for 50 bytes, and then on the EVM will take this 50 bytes out of the memory and write them into the permanent storage of this contract's code, which then never can be changed anymore. So that's basically what a constructor does. Yeah, that's the simple version. Any questions about this? Otherwise, we can also.
Firewall application.
Yeah, I have a question regarding that. While looking at the upgradability proxy, that the ZOS has, so they have also this function where it finds this free memory. It finds it from the 0x40. So is this the reason for it to find that free pointer?
Yep. So I don't know exactly what right. Yeah. So exactly that's the reason why it looks in that location, because basically people have agreed that that's where it is. But in the future it might change. In the future it might be anywhere, or there might not be a free storage pointer anymore.
Yeah, because in the previous version it was 0x40, and the new version doesn't have it has 0x00. So
okay.
does it make any sense, or?
Oh yeah, I'm actually not aware of that. I need to check afterwards.
Sure.
Yeah, can you send me the link, then I can check afterwards.
Sure, I'll do that.
Yep. Okay. Just so this, for those who don't know it, I'll make it a bit bigger. So this is Remix. So we have the contract on the left, and here we kind of have the individual steps of the contract, and because it's always, so we see the stack kind of changing below, and it's always a bit tricky to keep track of what's on the stack, right? Because we pushed it somewhere, like we jumped to kind of the end of the constructor. It's always a bit tricky to keep track of what's going where. So why I'm bringing this up is I wanted to show two things here. So first of all, when we go to the end, wait, sorry, I'm in the wrong transaction. We'll deploy again. This one, and I need to scroll down here. Doesn't work. Debug. Okay, so this is now the constructor in Remix. If it would do anything, no, it doesn't. Yeah, okay, that's classic Remix.
You removed the contract, so.
But I deployed it again. I have it.
Yeah, but the transaction. Yeah, okay.
Yeah, but I'll clean up everything and try again. I think it's not showing me the right transaction probably. So one last try. Okay, yeah, now it works. Doesn't work. Maybe it works. Okay, so just to quickly show this, so because it's always tricky to keep track of what's actually on the stack, that's why tools like Remix exist. Unfortunately, it sucks balls. Yeah.
Just hard refresh.
Yep. It worked, of course, when I tried it before, but yeah, it's Okay, we'll ignore that remix ever existed and go back to the presentation. So yeah, we saw what the constructor does. You had another question about the constructor, or?
The DAP.
Yeah, the DAP, right. So the application, I mean, here, as we figured out, this one was completely useless, right? So this copied the call value, which then later we just removed again. But for example, this one we need because we need this value twice. First we need it for code copy, and then we need it for return.
Doesn't algorithmically double things, it copy pastes the same thing twice on the stack.
It copy pastes the top thing. Well, for DAP1, it copy pastes the top thing again on top.
Yeah, okay. I thought it was doing algorithmic doubling.
No.
DAP3 would copy the third element on the top.
Yes, and that also brings me to another important point, so there's DAP and there's swap, and we didn't see a swap, but swap you see very commonly on these in the bytecode, and DAP1 takes the first stack element and duplicates it. So if there's like a number 3 on the top, now there's a number 3 and a number 3 again. And swap1 takes the second element and swaps it with the first one, which can be or at least in my mind can be confusing, because now if you have DAP3, it takes the third element and duplicates it. But if you have swap3, it takes the fourth element and switches it with the first one. So that's why it's important to keep this in mind, and can be quite confusing. And it of course keeps going like for the other ones. So yeah, DAP and swap, the number actually means something different, but there's 16 for both of them. So there's DAP 1 to 16 and swap 1 to 16. Okay, good. So now we come to the actual code. So what's being executed when I call my code that I just successfully deployed. So again, we have the exact same thing. We are storing the free memory pointer. And again, we have the exact same thing. We're checking if there is ether being sent to our contract, because we have actually we didn't follow the other path the other time, so we can do it now. So if there's ether being sent, then call value will be bigger than 0. So then this is 0 here will return a 0, right? Because it's not 0. So we will not jump here, which means we are going to these 3 instructions and we are reverting. So basically, whenever we're receiving ether in this contract, we're reverting. And that's because none of our functions are marked as payable. So you need to mark your functions explicitly as payable in order for them to allow to receive ether. Otherwise, basically, we have the same thing that we had before until this pop. And now it becomes a bit more interesting. We have this. Now is the part where we are selecting which function we want to call. And here we only have one function, and it's called f. And so basically here, right, before that, we again have another check. So we need to start here kind of in the innermost layer. So we have a check for call data size. So call data is basically the input to the EVM. So whenever we do a message call, we can pass a data, which is called call data, and call data size just gives us the length of this data. And we are basically comparing the size of this data to the number 4. And if the size of our data is less than the number 4, we're jumping to tag number 2. And we can quickly check. At tag number 2, again, we will revert. Basically, we are pushing 0 on the stack. We're duplicating the 0. So now we have 2 zeros on the stack, and we revert, meaning we revert without an error message. because instead of the 0, we could have an error message there. So why the hell are we doing this? Again, convention. Because there is a convention that if we are calling one larger, if we're calling a function, we will as the first 4 bytes of the data put the hash of the function signature. So there might be arguments in here. And here the first 4 bytes of the string f with brackets is 2612 and so on. So that's what, if we want to call function f, that's what we need to put in the first 4 bytes of our call data. And if we don't have a fallback function, then every call basically has to contain at least 4 bytes. So that's why we have this check here. If it doesn't contain 4 bytes, then we're not even continuing. Then we can make use of the glorious new opcodes. So this is shift right. So basically the problem is we now have 30, like everything is 32 bytes. So we do a call data load, which means we are fetching the first 32 bytes of the call data onto the stack. But the first 4 bytes are here, and like among the whole 32 bytes, they're kind of in the beginning. So we want to move them all the way to the right, so we shift right. And we shift right with the correct amount here. And then we have the 4 bytes of the function we want to call, basically. We are saving this once, and then we're comparing it to this value, which means, like in this case, first we're comparing to, do we want to call function f? And if we want to call function f, then if this is equal, then we're gonna jump to tag number 3. So if there would now be more functions, if we wouldn't just have one function f, if we also had g and h and so on, then we would have like many lines looking like this, where we always compare to like one hash. We see if it's equal, and we jump to the respective function. Here we only have one function, and it's extremely boring because it's doing absolutely nothing. So here it's kind of tricking us a little bit because it will just end up jumping around a bit more. So for those who are interested, this is not really interesting because, yeah, it's an empty function, but it will push tag 4 on the stack, tag 5 on the stack, jump to tag 5. Then here, because tag 4 is still on the stack, jump to tag 4, and then we reach the stop. So stop is the point how we stop how we do a regular stop in EVM, so like a non-reverting stop. So yeah, that always basically has to be the last instruction or a return. And then finally we have this garbage looking string down here. So this is this auxiliary data, which among other things contains the swarm hash, which you can use to figure out what kind of contract this is, but it's not really being used a whole lot. It basically contains a hash of the deployed bytecode. But yeah, it's a kind of leftover from old times. Yeah, so that's basically what happens when you execute a smart contract. These are all the little things that happen in the background, even for an empty smart contract, and of course for a big smart contract where there's actual data in it, a lot more things than actually happen.